Okay, we are online. Good morning, good afternoon, or good evening, depending on the place of the earth where you are now. We are starting now the 4th day of our professional training on GNSS, signal processing and navigation techniques, organized by Galileo Information Center Brazil. Welcome everyone that are already connected to us, and I would like to thank Professor Jaume Sanz Subirana, Professor André Almeida, and also Professor Adrià Rovira Garcia. Thanks for your presence here in this professional training. Today, who is going to present is Professor Jaume in the first part, and Professor Adrià, the second part. Good morning, good afternoon, welcome.
Hello, good morning. Hello, everyone. Bon dia a todos. I'm going to share my screen.
Okay, everything is okay. We are seeing your screen in the edition mode and now in the presentation mode. Everything is okay, Dr. Jaume? If is there any problem with your screen sharing or with your audio, I will open my microphone and I will tell you.
That's right. Thank you so much. Okay, this lecture is an overview of the GNSS positioning techniques. This is the layout of this presentation, this lecture. The idea is to give a general idea about the different positioning techniques and to give some idea about what we can expect, which accuracy, which performance we can expect from these different techniques. We will start with the standalone positioning, then we will talk a little bit about differential positioning, and then we will go to the code-based differential positioning and carrier-based differential positioning. In carrier-based is where we have the highest accuracy we can achieve. We will talk about real-time kinematics, RTK, and precise point positioning. Then, standalone positioning, as you know, this is the basic positioning technique we have. Standalone positioning is the positioning that we can get in our mobile phones, in the mass market mobile phones or mass market receivers. And the idea of standalone positioning is GNSS receiver autonomous positioning. Autonomous positioning means to use only the signal transmitted by the satellites. Let's say we use the ringing and the navigation message. The ringing, the measurements of GNSS receiver about the traveling time from satellite to receiver. This is the ringing. And the navigation message in order to know the satellite coordinates. Well, the accuracy we can expect in this positioning is based on code or in a smoothed code. The accuracy is at the level of few meters. Here we have some nice examples. This is kinematic positioning. Kinematic means single epoch positioning. Kinematic means that we have an independent solution each epoch. Then this is the accuracy as a function of time in the vertical, as a function of time for the north, east, and up is vertical component of the error. And as you can see, this is a nice figure. Using only code and using only broadcast orbits and clocks, we can achieve few meters level positioning. And this is in the horizontal domain. It depends, of course, on the satellite geometry. The highest accuracy we can achieve is in differential positioning and using not only differential positioning, but also using carrier phase measurements. Along this presentation, we will talk What does it mean? We will remember what does it mean code-based measurements or carrier phase-based measurements. Then the highest accuracy we can achieve is in differential positioning, and differential positioning in general means GNSS augmented with data. This data could be differential corrections computed from a network of reference stations or measurements for a reference station. Then using this additional data, these differential corrections and measurements, we can remove errors, signaling space errors. And the idea behind this is that errors, and this is like a mantra, the idea is that errors are similar for users separated tens or even hundreds of kilometers. In this case, errors are similar for this user, reference station, and user, and this error can be removed, or mitigated in differential mode, improving positioning. To fully remove or just to mitigate, it depends on the baseline between the reference station and the user receiver. Well, these are general ideas. The highest accuracy we can achieve in differential positioning is applying what we call ambiguity fixing, for instance, using the RTK techniques, real-time kinematic techniques, and fixing the ambiguities, we can achieve centimeter level of accuracy. This plot is based on real data. And as you can see, the accuracy is at the level in the horizontal domain, north and east, is at the level of 1 centimeter, 1 sigma. And in the vertical delay, in the vertical component, typically the accuracy is about 3 centimeters, 1 sigma, which is a very, very good result in kinematic positioning. Kinematic in this case means let the coordinates free, means not to put any constraint to the coordinates. Well, this is the general view, standalone and differential positioning. Just remember ideas that has been presented in previous sessions. This is in order to fix the initial ideas. As you know, well, GNSS technique use triangulation to find the user location. And what does it mean, triangulation? This means that we have to solve a geometry problem where, well, in the ideal concept, we can assume that the user solution is in the intersection of different spheres, having in the center of these spheres the satellites, the GNSS satellites. Then we have to solve this triangulation problem where in order to compute this user solution, to compute this intersection, we have to know first where the satellites are, where the centers of these spheres are. Also, we have to know the satellite clock offset. This is because among the satellite location, we have to measure, we have to know the radius of these spheres. Let's say the ranking, the distance between satellites and receiver, the apparent distance. In order to measure this ranging, this pseudo range we use signals, code and carrier measurements, and these signals the measurements we use refers to 2 different clocks, satellite clock and receiver clock. Then any synchronism error between these clocks will introduce errors in the estimation of the traveling time of the signal propagation from the satellite to the receiver antenna. Traveling time is what we estimate in order to calculate this code or these carrier measurements. Well, you know well these ideas because they has been presented in the previous sessions. Then in order to solve these problems, we have to know where the centers of these spheres are. We have to know the radius of these spheres. Then the ranging, we will consider two different measures for the ranging. These measures and compute are based on the estimation of traveling time from satellite to receiver. And we will use code measurements, what we call code measurements, and carrier phase measurements. Moreover, the signals from satellite to receiver are contaminated by different error sources. These error sources are atmospheric propagation errors. This is because the signals propagates through the atmosphere. This means the ionosphere, troposphere. There are relativistic errors because the clocks, the satellite clock and the receiver clock, are at different locations and under different gravitational potentials, and this introduces relativistic effects. There are clock offsets because these clocks are not perfect and accumulate offsets along time, instrumental delays, and so on. Then there are different errors that contaminates these measurements, and we have to take into account in order to properly model the measurements we use to solve this triangulation problem. Then, from the conceptual point of view, this looks very easy. This is just to solve a triangulation problem, but as we know, the evil is in the details. Then, how important are the errors in satellite orbits and clock? As I commented, we have to know where the satellites are. Then we will know the satellite coordinates with a given error. We compute the satellite coordinates in the autonomous positioning. We can compute the satellite coordinates using the navigation message, the broadcast navigation message. This is the message transmitted, the message broadcast by the satellites. Then how precise are the coordinates and the clock offsets we can compute using the broadcast message, using the information transmitted by the satellite? Well, this is based on real data. Here we have plots in the top. The plots at the top corresponds to the broadcast data. And here we have, as a function of time for 24 hours, the errors in the radial, along track, and cross track components. Radial is in the direction of the air center. This is from satellite to air center, radial. Along track is in the direction of the motion, the movement of the satellite, and cross track is orthogonal to them. As we can see, the radial component, which is the most important for this positioning, the error in the radial component is about meter level. Here we have a plot for all satellites in view. This is why we have different tracks for all satellites in view in 24 hours for a given day. Then, as we can see, the error in the radial component is at the level of 1 sigma, 2 meters. Then the error in the cross track is quite similar, and along track, well, it depends on the satellite. But few meters level errors in the quality of the coordinates, in the accuracy of the coordinates we can compute using the navigation message, and this is for the clock offset. As I commented before, as you know, we have atomic clocks on board of the satellite, but although being atomic, although being highly stable clocks, they are not perfect and they accumulate drift along time. Then the navigation message not only provides to the user information about the errors in orbit, about the satellite coordinates, but also about the clock offset. Well, this is the accuracy. Here we have the accuracy in the satellite coordinates, and here we have the accuracy in the clock offset. Well, we can determine using the broadcast message the clock offset with errors at the level of few meters. This is what we use, broadcast coordinates is what we use for the code-based positioning. But as we will see in the last part of this presentation, we have also high accuracy positioning. For high accuracy positioning, in particular for precise point positioning technique, this is a technique that we will see at the end. We can use more precise products. These precise products can be computed by some centers, or, for instance, in Galileo, the high accuracy service will broadcast precise orbits and clocks. Then the accuracy of these products, these precise products that we will use for high accuracy and not for a standalone, not for the mass market. For high accuracy, the accuracy of these products is about 2 orders of magnitude higher than the broadcast. Here we have an example. The accuracy is about few centimeters. This is for orbits, and this is for clocks. But this is for high accuracy positioning. In the case of standalone positioning, here in this case we use broadcast orbits and clocks, with accuracy is at this level. Well, this is about the accuracy that we can have when we compute the satellite coordinates. The second thing is about the accuracy in the ranking in this code and carrier measurements. Well, as I commented, as you know from previous sessions, we used 2 different kinds of measurements: code measurements and carrier phase measurements. Code measurements are noisy. Here in blue, we have an example of code measurements. Well, actually, these are the preferred residuals. These are the code measurements after removing all what we can model, after removing geometry, after removing relativistic effects, and so on. This is the input for the navigation equations. Well, as you can see, code measurements are noisy, but are not ambiguous. I will explain better what does it mean not ambiguous, what does it mean unambiguous. We have also carrier phase measurements. Carrier phase measurements are precise. Here in red, we have carrier phase measurements. Here we have a zoom. Carrier phase measurements are precise, but are ambiguous. What does it mean ambiguous? It means that on one hand, every time we lost the signal, when we lock the signal again, every time we lost the signal, when we lock the signal again, there is a jump by an arbitrary number of cycles. This is what we call cycle sleep. Every time we lose the signal, when we get the signal again, there is a jump by an arbitrary amount. Then if we want to use carrier phase measurements, we have to repair these measurements. We have to repair this jump. This is what we call to fix the ambiguities. Remember that before I has been talking in fixing the ambiguities. I said, well, this is with carrier phase after fixing the ambiguities. We will explain along this presentation what does it mean to fix the ambiguities. Here we have a plot showing, this is based in real data, code and carrier phase measurements. In blue, we have code measurements. I said, as I commented, code measurements are non-ambiguous measurements. Non-ambiguous measurements are noisy, but they are not ambiguous. What does it mean? This means that here in this plot, we show a plot of the code measurements for a given satellite as a function of time. Then the value that we have, the value that the measurement estimate from the traveling time from satellite to receiver is an estimation of the apparent distance from satellite to receiver. What does it mean, apparent? Well, apparent because this distance, these measurements, as I commented, is contaminated by different error sources, clock synchronism errors, atmospheric propagation errors, and so on. This is why I say pseudo or apparent, pseudo range or apparent measurements. It is not exactly the geometric range. It is contaminated by this error, but it's an absolute measurement. This is a measurement of the apparent distance from satellite to receiver. As the satellite moves, this distance vary. Here the satellite is approaching, and here the satellite is going away, and here the distance is getting shorter, and so on. In the case of carrier phase, I commented carrier phase is ambiguous. Well, every time we have a cycle slip, there is a jump by an arbitrary amount, but even at the beginning, when the receiver locks the carrier, when the receiver locks the signal, there is an ambiguity in the value of carrier phase. For instance, if at the beginning, if the carrier is determined within the one cycle, then we will have this ambiguity, this distance between carrier phase and code. Then the receiver locks the signal, estimate the fractional carrier phase, and then accumulate cycles, As you can see, the pattern in carrier phase is the same that in the code. Here there is a cycle slip, here there is a jump by an arbitrary amount. Then, in order to use the carrier phase, we have to repair the carrier phase, and we have also to estimate the ambiguity. This means that it will be a little bit more complicated to use carrier phase than code. But if we are able to repair the carrier phase, we will have a very, very good measurements, because carrier phase measurement are about 2 orders of magnitude more precise than code. Then is precise, but is ambiguous. Well, these are the general ideas for the introduction. Well, code is noisy, but we can smooth the code using carrier phase. An example of a smoothing filter is the hatch filter. Here we show in green the raw code measurements, as you see, are noisy, and in blue the carrier phase. The pattern is the same, and we show in red the smoothed code. We can smooth this code, the green one, using the carrier, applying this, what we know, hatch filter. From the conceptual point of view, what the hatch filter do is in some way to estimate in real time the distance, to estimate the ambiguity, the distance between code and carrier, to estimate this distance, and then align the carrier with the code. And this is what we see in red, in real time. And this is what we do in real time. It takes some time to converge. Then This is not perfect. This is not, although in this figure it looks very nice, this is not perfect because there is an alignment error, and the accuracy of this smooth coat is typically about half a meter. It depends on the elevation of ray, but about half a meter. But this is not bad because it's better than having several meters of error. Then we have, as a summary, we have code measurements in green, carrier phase measurements 2 orders of magnitude more precise than the code in blue, and we have smoothed codes. When we smooth the code with the carrier and smoothed codes, the accuracy can be at the level of 50 centimeters, depending on it depends on the multipath, of course. Okay, let's go to, once we have been talking about the GNSS positioning and errors in the signal, we can go to the standalone positioning. As I commented before, standalone positioning is the autonomous positioning using only the signal from satellites without any augmentation, without any additional information. And this is based on code measurements or smooth code measurements and the broadcast message. In the broadcast message, we have information in order to compute the satellite coordinates. As we saw before, we can compute using the broadcast message the satellite coordinates with accuracy about 1 meter, 2 meters, and satellite clock offset. Here we have a layout of the errors in the signal. This is just a conceptual view. Well, the geometric range, actually geometric range goes from, geometric range is the Euclidean distance from the satellite antenna phase center to the receiver antenna phase center. This is a conceptual view. And this is about, for GPS satellite, about 20,000 kilometers. And we have other error sources. Sorry, here we have atmospheric propagation errors due to the upper layer of the ionosphere. This can reach from 2 up to 30 meters. It depends also on the ionospheric conditions also. This is in the nominal case, and it depends on the elevation rate. Tropospheric delay is at the same level. Then we have receiver clock offset and satellite clock offset. As I commented, these clocks are not perfect and they accumulate errors on time. Relativistic corrections, well, in fact, on factory, most of the effects due to the relativistic corrections on the satellite clocks are corrected, just tuning the frequency of the satellite, of the oscillator in the satellite, but it remains a residual relativistic correction that we have to take into account at the receiver level. This residual relativistic correction, after tuning on factory the clock oscillator on board of the satellite in order to remove most of the relativistic effect. The residual can be up to 30 meters. Okay, then in order to model the measurements, we have taken into account all these errors that contaminate these measurements and contaminate both code and carrier phase measurements. Here we have a layout of the effect of this error sources at the positioning level. And the idea is, okay, what is the effect? Which is the effect that produce the relativistic correction or ionosphere or troposphere at the positioning level? Well, in these plots we show in blue the solution with the full modeling. In all these plots, blue corresponds to the solution with the full modeling. That's it. That is, using, correcting, removing all these errors that contaminates the signal when working with code measurements. And in red, we show the solution neglecting each one of these errors. Well, as you can see, the most important one is the satellite clock offset. This is because satellite clock offset can reach hundreds of kilometers. What does it mean, satellite clock offset? As I commented before, although we have very stable atomic clocks, hydrogen masers on board of the satellite, although being highly stable, they are not perfect and accumulate errors on time. We have to take into account that just 1 nanosecond means nothing. 1 nanosecond of error means 30 centimeters when we scale this nanosecond with the speed of light. 1 nanosecond multiplied by the speed of light is 30 centimeters, and 3 nanoseconds is 1 meter. Then they accumulate errors, and the ground segment estimate this clock offset together with the satellite coordinates. Ground segment estimate this satellite clock offset together with the satellite coordinates, and this information, as I commented before, is sent to the user in the navigation message in order the user to allow to estimate, to calculate the satellite coordinates and also the clock offset. Then, if the user receiver does not take into account this clock offset, the error can be huge, at the level of hundreds of kilometers. Less important is the relativistic effect. This is the residual correction that we have to apply. Well, it's less important, but at the level of tens of meters, here up to 20 meters. Effect of the ionosphere, in red, we neglecting the ionosphere can be up to 30 meters, troposphere, hardware bias. What does it mean, hardware bias? Well, there are errors due to the hardware. The hardware in the receiver, in the receiver, user receiver, and satellite receiver, due to the event propagation, the signal in the cables. And also we have to take into account the coordinates at emission. What does it mean, this plot? It means that we have to consider the ray from the satellite location at emission time to the receiver at the reception time. Well, this looks obvious. Okay, if the signal travels from this point to this point, we have to model the ray from this point to this point. But the problem is that what the receiver knows is only the time when the signal gets the receiver. What the receiver knows is the time when the signal gets the receiver. And at this time, the satellite is at this different location. When the signal gets the receiver, satellite has moved and is at the reception time. Then we need some algorithm in order to estimate the emission time from the reception time. Then, neglecting this detail, we can get errors at the level of more than 100 meters. Well, differential positioning and differential corrections. Some of these errors can be cancelled in differential mode. Satellite clock, ionosphere, let's say. Differential positioning concept and differential corrections. As I commented before, the highest accuracy we can achieve is in differential mode, where the idea is that errors are similar for users separated tens or even hundreds of kilometers, and these errors cancel or can be removed or mitigated. It depends on the baseline. It depends on the separation between them in differential mode, improving positioning. Here we have the errors on the signal. We have errors on clocks. Errors on clocks are common, are the same. The same clock offsets are seen, the same satellite clock offsets are seen by the reference station user. They see the same errors. Orbit errors, ephemeris errors. Well, the orbit error depends on the user location, because what affects the positioning is the projection of the orbit error in the line of sight direction. If we have the satellite here, then what affects the positioning is the projection. Let me check. If we had, for instance, if we have the satellite here, what affects the user, this is the line of sight, and here we have the error. What affects positioning is the projection of this error in the line of sight. Well, in this case, because the satellite is at 20,000 kilometers, the projection will be the same. The error will be the same. The orbit error will be the same. But as the baseline, as the distance between reference station and receiver becomes large, this projection can vary, and then the projection can be different. Okay. Then there is a strong spatial correlation, but are not fully common, these errors. This is the same with the ionospheric delay. If the reference station and receiver are close, they see the same ionosphere, but as the baseline become large, they see different portions of the ionosphere, and then the errors can start to be different. We have weak spatial correlation of the troposphere in the case of the ionosphere, and we are working with code measurements. In nominal conditions, we can assume that the ionosphere, with code measurements, when we can accept errors at the level of few meters, we can assume that the ionosphere is mostly the same, up to 100 kilometers. In the case of the troposphere, there is a weak spatial correlation, and we can assume that is the same about 10 kilometers, not 100. Okay, and finally we have local errors, multipath and receiver noise. These are uncorrelated because are different receivers that can be different multipath and can have different receiver noise depending on the location and depending on the technology used by the receiver. Then what differential positioning attempts to remove or mitigate are these errors: clock, ephemeris, ionosphere, and troposphere. Let's see an example. I like to show this slide because the differential positioning, one of the motivations of developing differential positioning was what we have before the year 2000. Before the year 2000, we had in GPS what we call the selective availability. Selective availability was an intentional degradation of the public GPS signals, and it was implemented for use in national security reasons in order to deny the full capability of the GPS system to non-authorized, non-military users. This degradation introduced large errors at the user level. Here we show, this is based on real data, the errors in orbit, three-dimensional error, in blue, and the errors in clock. As you can see, the clocks, there was a process noise affecting the clocks and introducing these random errors in the clocks. And this produced at the user level positioning errors at the level of more than 50 meters. In the 2nd of May 2000, selective availability was removed and the performance improved drastically. This is the performance we have right now. Then, because at the time, because the selective availability was applied on clocks, and because clocks are the clock errors seen by the reference station and user are the same, are common, then using differential positioning, it was possible to fully remove this error. Let's see one example. Here we have an example based on real data. This corresponds to the time where we had this selective availability on. Here we have two receivers. This is Ebre station and Bell station. This is in the north of Spain. This is the border with France. Here is Spain. And here the baseline between these two receivers is about 100 kilometers. Two receivers separated 100 kilometers. Here we show the user solution for both receivers in X, Y, and Z coordinates. And as you can see, the pattern is mostly the same. This is the idea. The error seen by these receivers is the same, and this is why, mostly the same, and this is why the positioning error is similar. This is the idea. Then, if we compute the difference between this plot and this plot, between both solutions, we remove most of the errors. And this is the idea of differential positioning. Error is the idea, a conceptual idea. Then we have to refine. Errors are the same and cancel in differential mode. This is the idea. Then the first approach that we could consider in order to improve positioning, the first approach, then we will refine. The first approach in order to remove this error is okay, because both errors are mostly the same. We could consider as follow. We can consider a reference receiver with which coordinates are accurately known, which coordinates are known at the centimeter level, for instance. Using this reference receiver, we can compute the error in the positioning error, because we can compute the solution, the navigation solution from the satellites, and compare the solution with the coordinates, with the precise coordinates, what we know from the receiver in this reference station. And then, because errors at the position level, we have seen that errors are mostly the same, we can use this value in order to remove this error in the user receiver. Well, this is from the conceptual point of view. This is not the best way to proceed. And actually, in this approach, in this example, we can say that the differential error has been cancelled in the position domain, because this is in the position domain, at the user domain, just comparing the coordinates, the position coordinates. But as we know, the positioning error not only depends on the errors in the measurements, but also depends on the satellite geometry. Also, it depends on the satellite geometry. Then, in order to apply this simple approach, it is required to use the same satellite in both stations, because if we have different number of satellites, then the geometry will be different, and the error, the final error, can vary. A better solution is what we call range domain approach, and the idea is to compute for each satellite in view, to compute the error, the range domain approach error for each satellite in view to compute a correction. Then we compute a correction for each satellite in view. Well, we have the reference station and with known coordinates. Then we have the navigation message, and then we can compute the satellite coordinates using the navigation message. Because the navigation message is not perfect, the broadcast position computed in the navigation message will be different from the actual position, but well, then using this broadcast position, we can compute the geometrical distance, the geometrical range. In this geometrical range, we will have information about the error in these coordinates because we are using these coordinates, not the true coordinates. And then also using in the measurement, in the pseudo-range measurement from the satellite to reference station, in this measurement we will have information about other errors, atmospheric propagation error, which will be quite similar for the user, but it depends on the baseline. In this measurement, we have information about the atmospheric propagation errors, relativistic errors, and so on. Then using this information for each satellite in view, where we have information about the error in the satellite coordinates using the broadcast, and errors in the pseudo-range due to the satellite clock offset, atmospheric propagation, using this information, we can compute a correction, satellite correction, and then the reference station can compute the satellite correction for all satellites in view and send these corrections to the user. And the user can apply these corrections in order to remove the signal in space error and improve positioning. But this is the range domain approach. We compute corrections for each satellite in view. Okay, well, after this introduction, let's go to present code-based and carrier-based differential positioning. As you know, code-based means using code measurements. Code measurements, pseudo ranges, code measurements are noisy, but not ambiguous. We have not to repair the code measurements. We have only to remove the errors that contaminate the code measurements. And we have carrier phase measurements. Carrier phase measurements are about 2 orders of magnitude more precise than code, but are ambiguous. In the case of carrier phase, we have to repair these measurements. Okay, let's go to the code measurements. Well, this is the idea of differential positioning. Using code measurements, we can achieve about 1 meter level or better positioning accuracy for baselines up to 100 kilometers. Up to 100 kilometers, we can achieve about 1 meter level of accuracy, and using a smooth code. You remember, we have the code measurements, we have the carrier measurements, and we can reduce the code noise, smoothing code with carrier. Then using carrier smooth code, using this smooth code, and using the differential corrections compute from a reference station, we can achieve 1 meter level for user within up to 100 kilometers, user 100 kilometers far from reference station. And the idea is what I commented before. We have a reference station which coordinates are known, very well known at the centimeter level. Then, because we have the navigation message, we can compute the satellite coordinates using the broadcast message. as we've seen, these coordinates are not perfect. We've seen that using broadcast message, the error in the coordinates is about 1 meter level. Then this is the actual position, and this is the position that we estimate using the message. Then, because we know the satellite coordinates, we can compute the geometric range, distance from satellite to receiver. And in the geometric range, we have information about this error, the satellite coordinates error. And we have the measurements, the pseudo-range measurements, smooth code. In these pseudo-range measurements, we have information about clock offset, which is the larger error. We have information about atmospheric propagation errors and information about relativistic effects. This is here. And then the correction that we can compute for each satellite in view, the correction that the reference station compute, the satellite in view is what we call reference pseudo-range corrections, PRC, pseudo-range correction. And this is just the geometric range, the Euclidean distance from satellite to receiver, minus the pseudo-range. And this is the correction. We can also compute the range rate corrections. This is the variation on time. This is the rate, the variation on time. And these corrections can be sent to the user, and the user can apply these corrections to their measurement, to its measurement. The user can apply these corrections to the measurement, to the user measurements, in order to remove signal in space and improving in this way the positioning accuracy. Let's see an example. Let's see how it works in a real base data example. Here we have 3 receivers. This is in Goddard. This is in USA. We have 3 receivers in USA. This is in Maryland. And the baselines are 76 meters, let's say meters, between GODN and GODS, and kilometers between GODS and USN3. Here we have 2 different baselines. Here the data was collected in the current situation where the selective availability is disabled. Here we have not selective availability. Well, now the error is at the level of few meters, not 60 meters, not 100 meters, like as at the time where we had the selective availability. Now the error is small, just meters, but you can see in this plot, this is a standalone positioning. This is using only the information sent by the satellite, ranking and navigation missile. Here we have for the 3 receivers in green, this is the reference station that we will take, receiver in blue, and receiver in red. Here we have the standalone, the autonomous solution for each one of the receiver. As you can see, solutions are very similar. This is in the vertical. This is the vertical error, vertical component. As you can see, the idea that we have presented before, errors are similar for receivers, close receivers, and this is the idea. Even in this case, here we have kilometers, and here we have meters. Then this is the vertical component, and this is in the horizontal, on the horizontal component. And here in the bottom plots, we show the differential solution. In blue, we show the differential solution for the receiver in blue regarding to reference station. This is baselines are meters, and this is the solution for the receiver in red regarding to the reference station, which are kilometers. Receiver in blue, meters regarding to the reference station, and receiver in red regarding the reference station, kilometers. What we see? Well, errors are similar, but and can be removed or mitigated in differential mode, but it depends on the baseline. As the baseline becomes larger, the similarity becomes lower, and this is mostly due to the atmospheric errors. As you can see, for the large baseline, we have a strong mitigation, of course. Here we have errors more than 1 meter, and here is under 1 meter. There is a strong mitigation, but we have larger error for the larger baseline than for the shorter baseline. Then the mitigation, as we commented before, depends on the baseline, because the errors are more similar when the baselines are shorter. Okay, this is the idea. Here we show the corrections. As we commented, we remove signal in space error using these corrections, these pseudo-range corrections. And these corrections are computed in this way, geometric range minus the pseudo-range. Well, here we remove the satellite clock, but this is a detail. Just taking the average of all corrections, but this is a detail. How looks the correction that we have to apply in order to remove the error? How these corrections, how this pseudo-range and range rate corrections looks? Well, these are the pseudo-range corrections for the different satellites in view. What we see here is that they vary smoothly. The variation depends on the elevation rate. In this case, for the satellite, this is satellite GP satellite PRN2. This is having the large variation, and this is because this is a low elevation satellite, and when we have low elevation satellite, the variation of the atmospheric effects is larger due to the variation, the obliquity factor, let's say. But the idea is they vary smoothly, and the rate, these are meters second, the rate, the variation on time is really small, centimeters by second, centimeters per second. This is how these corrections looks. Okay, let's go to fixed ideas. At the beginning, we had a standalone positioning. This is a standard point positioning. Here we have positioning errors at the level of few meters in single epoch. What does mean single epoch? This means that we have an independent solution every epoch. The current epoch is disconnected from the previous. We are not using information from previous epoch. This has been computed using less squares, just computing an independent solution every epoch. Few meters, single epoch, worldwide. There is no limitation in the user location. We can achieve similar. It depends on the user location, of course, but because it depends on the satellite geometry, and it depends on the ionosphere, the ionospheric activity, but in nominal conditions, we can achieve similar results worldwide, at every point in the planet. There is no limitation in the user location. Code-based differential positioning. Well, here we have, as we commented, a reference station that compute differential corrections. These corrections are sent to a user receiver, and the user apply this correction in order to remove and mitigate these errors. And the idea, the mantra that we repeat and repeat like a mantra, is that the errors are similar for users separated 10, even hundreds of kilometers in the case of code positioning, and they can be removed or mitigated in differential mode, but we have to expect some degradation with the baseline. Then we improve accuracy. We can achieve meter level regional area up to 100 kilometers in single epoch. Again, this works in single epoch. We can compute an independent solution each epoch. This means we have not to wait in order to restart any navigation filter. We have not to wait for the navigation filter to converge. No. We compute the solution with less square in single epoch. But look at here, there is a limitation. There is a limitation in the baseline. Here is worldwide, but here we have to be close to the reference station. We have to be close to the reference station. Using a smoothed code, we can achieve meter level up to 100 kilometers from reference station. Well, other differential GNSS using a smoothed code are the safety of life application. I mean to the ground-based navigation systems and satellite-based navigation systems. The local area, ground-based ground-based augmentation systems and satellite-based augmentation systems. But here, this augmentation system, this differential positioning, also use smoothed code as in the previous case, but here for this augmentation system, the main target is not to improve accuracy. The main target is not to improve accuracy, but to provide integrity. These are safety of life system. These are for safety of life application, like avionics, civil aviation. And the target here is not only to improve accuracy, but also, and this is the main target, to provide integrity. What does integrity means? What does integrity means? Integrity means that the system has to aware the user, has to inform the user in case of having any anomaly in the signal. The system has to protect the user. This means in case of detecting any anomaly, the system has to send the user timely alarms, to provide timely alarms in case of any GNSS signal failure, but not only provide alarms, but also to provide information to the users in order to allow the user to have an estimation, an idea of the level of trust the user can apply to the signal. In order to have this information, in order to compute confidence bounds, in order to say, okay, this is the level of confidence that we can apply to this information. What does it mean? It means that, as you know, for instance, in this aircraft, the pilot can have a GNSS receiver, and in the GNSS receiver, the pilot can have the aircraft coordinates. But what the pilot needs is an idea of the error of the accuracy of these coordinates. Well, what this system provides to the user is what we call protection level. We cannot know how accurate. We cannot know in real time what is the error in the receiver coordinates, but these safety of light systems provide to the user, provides to the pilot confidence bounds. confidence bounds as an estimation of the error, of the positioning error. And these confidence bounds are, it depends on the navigation mode, but for the CAT1 are at the level of 10-7. What does it mean? This means, okay, we have no idea about the error, but the system can assure that the probability that the true error goes over these confidence bounds, these are called protection level, the probability that the true error goes over these confidence bounds, this protection level, is 10-7, let's say 1 in 10 millions of cases. This is the idea to provide information to compute the level of trust to apply to the signal. Not only provide alarms in case of an anomaly, but also provide to the user information about the quality about these errors. Well, we have, as you know from the previous sessions, we have ground-based augmentation systems. This is for on airport application, and ground-based augmentation system involve a set of redundant receivers, typically 3 or 4 redundant receivers, and this is the reference station. And the reference station, on one hand, is monitoring the satellites in order to detect any anomaly, and on the other hand, because we have redundant receivers, the receivers are cross-checking themselves in order also to detect any anomaly in the receivers. And using this reference station, the GBAS, ground-based augmentation system station, can detect anomaly and send timely alarms to the user, and also compute differential corrections and integrity data. Integrity data means sigmas to compute these confidence bounds. Then alarms and integrity data. Well, here we have examples. I will not extend the explanation. And this is the same for weight area. Ground-based is only for an airport, and the coverage is up to 40 kilometers, This is limited by the radio link, 40 kilometers, but this gives navigation on the airport. And weight area is for continental service. For weight area, we have the satellite-based augmentation systems. In USA, WAS, weight area augmentation system. In Europe, EGNOS, and there are other augmentation systems for other regions. The idea of weight area augmentation system or the satellite-based augmentation system is to cover a weight area, like USA or like Europe. We have a network or reference station with separation with baselines can be hundreds of kilometers, even 1,000 kilometers. And using these reference stations, the system monitor all the data in reference stations are sent to the master station, and the master stations analyze the health, the satellite healthy, and in case of any anomaly, send alarms to the user, and also compute these confidence bounds, differential corrections and confidence bounds, to allow the user improve accuracy, and what is most important for the safety of line systems, have compute protection levels, compute these confidence bounds. Well, here we have an example. This is the EGNOS system. Here we have the reference station. This is the coverage. Here red means good. Here red means good. And here we have the error and the protection levels. Well, this is a Stanford plot. Well, Stanford plot, here we have the error, blue. Here we have the protection level, here in red. And the error must be always under the protection level. The error must be always lower. Error must be always lower than the protection level. Protection level must be larger. Then The solution in this Stanford plot must be always here. This means no problem. If any solution in blue goes over the red, this means this will be to this part of the diagram, and this means misleading information. This means problems. If we have any in a pixel here, this means that we have a problem. We have an integrity failure. But these systems are safe. Okay, this is for code-based augmentations system. Carrier-based differential positioning. This is the last part. Well, as I commented before, the highest accuracy we can achieve is using carrier phase. As you remember, the idea of carrier phase. Carrier phase is 2 orders of magnitude more precise than code. But this is the good thing. 2 orders of magnitude more precise than code, but it is ambiguous. This means that just from the beginning, there is an ambiguity in the value of carrier phase. It is not a direct measure of the distance between satellite and receiver. And every time that we lose the carrier, there is a cycle slip and there is a jump in the carrier phase by an arbitrary amount. This means it's a very precise measurement, but we have to repair these measurements in order to be used for navigation. Then everything will be a little bit more complicated. But if we are able to repair the carrier phase, we will achieve centimeter level of accuracy. Well, there are 2 main techniques. These are the classical techniques. Main techniques: relative positioning, RTK or network RTK, and precise absolute point positioning. PPP, precise point positioning with ambiguity resolution, or fast PPP. Well, in the case of relative positioning, in the case of RTK, we need at least 2 receivers. We need at least a reference station or user receivers. And this is the classical RTK, reference station and user receiver, and we estimate the baseline vector from reference station and user receiver. But also we can also consider a network of RTK where we have a network of receivers. And here in RTK, the idea is to make use of the idea we have presented before. Errors are similar for users separated tens of kilometers and can be removed or mitigated in differential mode. In PPP, in precise point positioning, we need only a user receiver, but we need a user receiver. It uses a single receiver, but we need additional information. We need additional information that corresponds to the precise orbits and clocks. Remember, at the beginning of this presentation, I have been shown the accuracy of orbits and clocks using broadcast orbits or using precise products. In the case of precise products, these orbits and clocks are accurate at the centimeter level, few centimeters. Okay, in PPP, we will use not the broadcast message, because the broadcast message, the accuracy is meters, the error in orbits and clocks are meters, few meters. We will use precise products, precise orbits and clocks, accurate at the centimeter level. We need everything at the centimeter level because the target is to achieve centimeter level. And then if we want to achieve centimeter level, everything must be at the centimeter level. This is why we cannot use here broadcast products. We need precise products. Although using a single receiver, this is also differential positioning. Why I say differential positioning? Yes, this is differential positioning because the user receiver is we compute the user receiver using the positioning relative to the network of stations used to compute these corrections, to compute these precise orbits and clocks. Then everything, the correction refers to the network, and this is also differential positioning. But it's absolute positioning, because here we compute the coordinates, the absolute coordinates of the user. Here in RTK, we compute the baseline vector, but also if the reference station coordinates are known, using the reference station coordinates and the baseline vector, we can also compute the absolute coordinates of the user, of course. Okay, let's go to see in more detail this. Well, this was the starting point, code-based positioning, and now we move to carrier-based differential positioning. Sorry, I touched the wrong, okay, then in using code we have few meters. Here in RTK we will have the highest accuracy, this means centimeters, few centimeters, and in PPP, precise point positioning, using precise orbits and clocks, we will achieve centimeter, decimeter level accuracy. This is for local area, we will talk about this, and we will need few seconds, this is not in single epoch, and this is worldwide, there is no limitation for PPP, again it's worldwide, but it takes longer to get an accurate solution. Let's go to see this in more detail. Let's go to real-time kinematics, RTK. Relative positioning, real-time kinematics. Well, the idea of RTK is we have a reference station, we have a user receiver, and using a radio link or cellular phone, using a radio link, the reference station send the measurements, the reference station measurements, to the user receiver, and the user receiver combine its own measurements with the reference station measurements in order to remove common errors and improve positioning. Also, because this is carrier phase based positioning, user receiver has to fix the ambiguities, has to repair the carrier phase. There is a limitation in the baseline between reference station and user receiver. The limitation is mostly due to the ionospheric error. In this case, everything must be at the centimeter level of the error. Then at the level of few centimeters, let's say, everything. Then the error component most difficult to model or to cancel is the ionosphere. The ionosphere can reach up to 10 centimeters in 10, 20 kilometers. It depends on the user location. And this involves a limitation in the baseline. Well, you remember this slide. We use carrier phase. Carrier phase is precise, but we have to repair the carrier phase. We use carrier phase because everything must be at the level, at the centimeter level. And the noise in carrier phase is less than 1 centimeter. Thermal noise is millimeters. Multipass noise less than 1 centimeter. That's perfect. Well, in RTK, what is the idea? In RTK, real-time kinematics, we need a reference receiver. And in RTK, the idea is to work in what we call double differences of measurement. This is the only slide with having equations. In RTK, we use double differentiate of measurements. What does it mean, double differentiate? This means that we take differences between pairs of receivers, between the measurements of pairs of receivers and pairs of satellites. We use a reference receiver and a reference satellite, and we take differences between satellites for a reference receiver, between receiver and reference receiver. For a given satellite, we take references. For the same receiver and reference receiver, we take differences between satellites. This is, at the end, we take differences between pairs of receivers and pairs of satellites. Why? This is in order, taking double differences, we get the ambiguity. Taken in double differences, the ambiguities are integer numbers of wavelengths. I'm going to explain better. The ambiguities, as I commented, we have to refer the carriers. The ambiguities contains an integer valued term, and real valued term. The ambiguities contains this term. This term is a given number of an integer number of wavelengths, and this term is an integer number of wavelengths. This is signal wavelengths, and plus this term that depends on satellite and receiver, we have two real valued terms. This is the hardware bias, carrier hardware bias for the receiver, and this is the carrier hardware bias for the satellite. The good news is that we can split the ambiguity term in this way. And the good news is that this hardware bias depends only the receiver and this only the satellite. Then taking differences between receivers, we remove the common term, the hardware bias common, that depends on the satellite, and taking differences between satellites, we remove the common term for the satellite, which is the hardware bias for the receiver. Then in double differences between receivers and satellites, we remove these terms. And what we have in double differences, this means double differences, what we have in double differences is an ambiguity, which is an integer number of wavelengths. And this is important because we can take benefit of knowing that in double differences between satellites and receiver, we can take benefit that this is an integer number of wavelengths. And then if we are able to have an estimate of this ambiguity with noise smaller than the one cycle, then we can estimate the exact value of the ambiguity just rounding up. Then we can take benefit that this is an integer number and double differences, and then we can obtain the integer value, the exact value of the ambiguity, just rounding up a raw estimate of this ambiguity. Well, there is the lambda method, which is a powerful technique that uses the correlation between the different ambiguities, but the idea at the end is this. Well, in double differences, because we are taking differences, we remove the errors, but we take the benefit of the integer nature of the ambiguities. Well, the problem can be there is a limitation in baseline due to the ionosphere. The ionosphere in nominal conditions, well, we can assume that up to 10, 20 kilometers, the ionosphere is the same, but in perturbed conditions, under ionospheric storms or under scintillation. In Brazil, there is a strong problem of scintillation. The ionosphere can introduce large errors that makes that this technique have problems to properly work. Then the ionosphere can be a threat. Well, this is the accuracy that we can achieve. 1 centimeter in 1 sigma for the horizontal component, 3 centimeters, 1 sigma vertical component. This is when we fix the ambiguities with RTK. Well, the idea is, as I commented before, to fix ambiguities. Then the performance depends on the initialization time, let's say the time that we need in the filter in order to start fixing the ambiguities, and the correctness of these ambiguities, let's say the reliability of these ambiguities, this ambiguity fixing, because any error in the ambiguity fixing can introduce large errors in the solution. Then we must be sure that the ambiguities are properly fixed. For typical baselines of 10, 20 kilometers, it depends on the user location. In few seconds, in 10, 30 seconds, we can achieve centimeter level of accuracy. Well, but just 2 ideas more about RTK. The main problem of RTK is the limitation in the baseline, 10, 20 kilometers, in order to fix the ambiguities. But this means that if the baseline is limited to 10, 20 kilometers, we will need many reference stations to cover a large region or even a country. For instance, we need about 30 stations to cover 10,000 square kilometers. This means for the European island, Corsica or Cyprus, we need many stations. But they would need, well, this limitation comes mainly from the ionosphere and troposphere as well, and also, but a little bit due to the orbit. This limitation can be overcome using a network of reference station. What does it mean? Then, using a network of reference station, we can estimate a propagation model, atmospheric propagation model, and using this atmospheric propagation model, we can remove these errors. And this leads to the virtual reference station concept or virtual reference station concept, let's say. This is one of the implementation of network RTK. This leads to the network RTK, and one of the implementations is the virtual reference station. The idea is we have a network of stations. Using this network of stations send the data to a central processing facility, and the central processing facility estimates a propagation model, atmosphere propagation model. Then the user goes into the coverage area, into the area, and estimates its position using code with an error of meters. This is not critical, and send its position to the central processing facility, and the central processing facility, using the propagation model, emulates a virtual station close to the user. This is not a real station, but using this propagation model and the information that have from the network station, emulates a virtual station close to the user, just very close, and the user can proceed the navigation, the survey using this virtual station, which is close, and can proceed in the normal way without needing to upgrade anything in the software. This is the idea. Because this station is closed, there is no problem with the atmospheric propagation. The atmospheric propagation errors has been estimated by the station. That's it. Well, again, this improve. This can allow us to extend the baseline from 1020 to 50 to 100 kilometers, which is a lot. It depends on the geographic location. We can extend the baseline from 15 to 100. It depends on the geographic location and the level of the ionospheric activity. But still, there is a limitation because 100 kilometers is not 1,000. It's not too much. There is a limitation. And we have to deploy many stations in order to cover a wide area. For instance, in order to cover 10,000 square kilometers, we need from 5 to 10 stations. The user is limited to the coverage, the data link coverage, system latencies. The availability depends on the network extent. We can work only in the region where the service is provided. And in the case of the virtual reference station, in this particular implementation from Trimble, this is a two-way communication. Two-way because the user has to send the coordinates to the master station, and then the master station send the corrections to the user. Two-way communication means that the number of potential users is limited. Okay, last one. Well, I will need about 10 minutes more to end. Last one, precise point positioning concept. Okay, we are here. In the first case, sorry, we can achieve few centimeters, but in few seconds, 10, 30 seconds, quickly. It's not single epoch. This is epoch by epoch. This is epoch by epoch. It's not single epoch, but mostly in few seconds, 10, 30 seconds, we can achieve centimeter level. But there is a limitation, few kilometers. PPP. In PPP, we will see this is worldwide. There is no limitation. Again, we have worldwide. There is no limitation. The accuracy will be a little bit worse, centimeter, decimeter level. And the main problem is that it takes longer to converge. In order to achieve the centimeter, decimeter, we need the best part of 1 hour. Okay, in this case, we use, as we commented before, precise orbits and clocks instead of a reference station. Well, the history, the PPP was proposed at the end of the 19th by Sundberger. At that time, this is a method for absolute positioning with a single receiver, as we commented before. And at the beginning, it was a technique that was developed for post-processing mode, not for real time, for post-processing. Now, and this is because the precise products, precise orbits and clocks at that time, they were not available in real time. Now, precise orbits and clocks are available in real time, and we can use this technique in real time. But this is important. In this technique, we need a very accurate modeling. Very accurate modeling because in the previous case, because reference station and user are close, taking differences of measurements, we remove common errors. Ionosphere, troposphere, solar and lunar solid tides. We will see what are solid tides, but here not. Here we have to model everything as much as possible. An accurate modeling at the centimeter level. We will see what does it mean, this accurate modeling. And we need dual frequency receiver. We need dual frequency receiver in order to remove the ionospheric error. The ionospheric error is the error component more difficult to model, but the good news is that the ionospheric error depends on the frequency of the signal, and using signal in two different frequencies, it is possible to mostly remove 99.9% of the ionospheric error using the iono-free combination. Okay, then accurate modeling and dual frequency. measurements. This is the performance. In static, we can achieve centimeter level. Static, what the static do is in some way to average the solution, and we can get in 24 hours centimeter level. And in kinematic means we let the coordinates free instead of averaging. In kinematic, we let the coordinates free each epoch. This is why the performance is like this. But we need some time for the ambiguities to converge. We will study this in more detail in the lecture tomorrow, when we study in detail the PPP. Centimeter level in static, decimeter level in kinematic, but the problem is it takes longer to converge than the RTK or network RTK. Look at this. These are 10,000 seconds. This is more than 2 hours. In 1 hour, we are here. Okay, as I commented, the ionosphere depends on the frequency, and more than 99% can be removed using a combination of signals into frequencies. As I commented, PPP, now there are different centers providing real-time orbits and clocks. Here we have an example from the products from EUREF, and then we can achieve decimeter level of accuracy. In the Galileo is developing the high accuracy system. Galileo ESA will start the first test for the high accuracy and implementing the PPP. Then we will have signal for high accuracy signal to implement PPP in real time from the Galileo satellites. Well, the positive thing, what is positive in PPP is it is worldwide. There is no limitation. There is no limitation in the user location worldwide. There is no limitation in baseline. And only a reduced number of reference stations is needed. For the whole planet, some tens of reference stations can be used. The modeling is more close to the physics of the problem. We use what we call state space representation, where the orbits and clocks are estimated separately. This is more close to the physical error sources, and this allows to broadcast this information with reduced message bandwidth. The cons is, as I commented, the large convergence time. And the accuracy is a little bit worse because because the ambiguities in PPP are not fixed. The problem here is that in PPP, we don't take advantage of modeling the ambiguities as integer numbers. Remember, in PPP, in RTK, we took the advantage of, in double differences, having the ambiguities. We can use the disadvantage that the double differences are integer number, and then we can round off, and in this way, fully fix the ambiguities. This is not the case in PPP because the ambiguity parameter that we estimate in PPP is a combination of the integer ambiguity plus the real valued satellite and receiver hardware bias. Then the ambiguity is the parameter that we estimate in PPP is a real valued parameter, not an integer parameter, real valued parameter. Then the integer property is lost. This is why we estimate the ambiguities as a real number. This is what we call to float ambiguities. The ambiguities are not fixed as a real number. The ambiguities are float. What we call float ambiguities? Well, because these are not the ambiguities, this is the user solution. But if we look at the plot, there is some oscillation during the convergence time. Well, but the if we wait after some time, after half an hour or 1 hour, depending on the satellite geometry, the float ambiguities will typically be close to integer. Then, if we can wait enough time, the solution can improve. But the problem is that, as I commented, is we need it takes longer. For very short observation times, we have to apply RTK. RTK is where we have the more important role for short observation time. Okay, then just a summary, a standalone. Okay, then let's go to have a summary of the whole presentation. Remember, at the beginning, we started with code-based positioning. This is standalone, and this is code-based. Standalone positioning, we have few meters of error, worldwide single epoch. In differential positioning, the baseline can be up to 100 kilometers, and we can achieve meter level. We improve from several meters to meter level. There is a degradation in the baseline, and the idea is that the errors are similar, users and cancels in differential mode. Main ideas are these. In the standalone, we use single frequency receivers, single frequency measurements plus broadcast orbits and clocks. We use only the information sent by the satellite, the signal and the navigation message. We achieve some meters level, some meters error, and we use code measurements or smoothing code. There is no ambiguity resolution because we are using code and not carrier. In differential positioning, signal errors are removed from the differential corrections. We use here single receiver with single frequency plus differential corrections compute from a station with known coordinates or nearby of a station. The errors are removed using this differential correction. There is a degradation of accuracy with the baseline, as we showed. And we use carrier smoothed code. Meter level, regional area until 100 kilometers, single epoch. Last one, the highest accuracy is with carrier phase. This is the accuracy. The highest accuracy is in RTK, few centimeters. Let's say more than 2 orders of magnitude than the standard point positioning. Few seconds is not single epoch, but in 10-30 seconds, depending on the satellite geometry, we can achieve this accuracy and limitation in the baseline, local area. In PPP, this is worldwide, like in code-based positioning, but it takes longer to converge. Best part of 1 hour, and we have centimeter of decimeter level. Last slide is this. Well, relative positioning use double differentiated measurement. In double differentiated measurements, because we use differentiated measurement, is the same single differentiated or double differentiated. Is the same in order to cancel common errors. Common errors are removed because we are differentiating the measurements from reference station and user. Is the same single differential or double differential here. And because we use here, it is important, because we use double differential measurement, ambiguities are integer numbers of wavelengths, and we can use this integer nature of the ambiguities in order to fix the ambiguities. This is not to have an estimation, it's to get the true value, and then we can fix the ambiguities as an integer number. In the case of PPP, the ambiguities are estimated as a real values. We cannot have the advantage of this integer nature because the parameter that we estimate is a real valued parameter. And this is what we call floated ambiguities. And this means that the solution takes longer to converge. But we need an accurate modeling of the measurements. We need dual frequency measurements and precise orbits and clocks. And this use a single receiver. In the lecture of tomorrow, we will analyze in detail PPP, and in particular, we will go to this accurate modeling. Okay, that's all. You have some references here, and if you have any question, okay, now is 17 minutes late. Okay, thank you so much for your attention.
Okay, thank you very much, Dr. Jaume. We have here 4 questions.
Oh, yes.
The first one from Tomás da Silva. Is the traveling time the same as the CMR age or correction age?
The travel, you mean the traveling time? For the carrier phase and for code.
Yeah, it's in the chat. Is a question from Tomás. Is the traveling time the same as the CMR age or the correction age? It's from the beginning of the presentation.
Yeah, well, in general, when we present the code and carrier measurements, in general speaking, we say code measurement is the traveling time from satellite to receiver multiplied by the speed of light. This is a simplification, of course. In the case of carrier, what we do is to estimate the fractional part of the ambiguity and then add the accumulate cycles. Then the approach is not exactly the same. And in order to estimate the code, what we do is, of course, this is more sophisticated. When I say this is traveling time, is in order to simplify, in order not to go into the details of the signal. But in the case of code, what you do is just to correlate the signal, the code, pseudo-random noise code from the satellite with a replica generated in the receiver, and with the time shift between both replicas, we can get the traveling time from satellite to receiver, and then this multiplied by the speed of light, we get the pseudo-range measurements. In the case of carrier, we do something similar, but there are more details. This is more in the arena of the previous lectures that were focused in the signal acquisition, and I has been presented this in a general speaking, without going into detail. Okay.
Okay, question from In. Actually, there are 2 questions. How long is the converge time of RTK, and if it is possible to replace GBAS with RTK in local area, like airports?
Well, it's different. The RTK, the convergence time for RTK, it depends on the user location, but and the satellite geometry. It depends on the baseline, but for short baselines, even in 10 seconds for short baselines, a few seconds, you can start fixing the ambiguities. It's very quick. Larger baselines or under perturbed ionospheric corrections, the situation can be worse. But typically between 10-30 seconds in nominal conditions and for not too long baselines, you can get you can start fixing the ambiguities and getting centimeter level of accuracy. And RTK and GBAS are different concepts. RTK, the target of RTK is accuracy, not integrity. And the target of GBAS is integrity, mainly integrity. RTK is based on carrier phase and ambiguity fixing. When we have to deal with ambiguity fixing, to guarantee integrity is really, really difficult. With ambiguity fixing systems, to guarantee integrity is really, really difficult. This is why the safety of light systems, the integrity systems of GBAS or SBAS, satellite-based augmentation system, or satellite-based ground-based augmentation systems, or satellite-based augmentation systems, these safety of light systems are not based on carrier phase, are based on smoothed code. Then GBAS is for airport operations. Is in GBAS provides differential corrections and sigmas and integrity data in order to allow the users to have not only more accuracy but also information on these confidency values. This is for avionics. The target is avionics. Are different applications, APB1 and CAT1, CAT2, CAT3 in case of GBAS, or in case of SBAS, CAT1 or APB1, APB2, are different approach modes, different modes with different requirements. GBAS, the requirements for GBAS and SBAS are very stringent because are safety of light applications, and there are life in the games, has to protect life. In the case of RTK, well, it is not a critical system. RTK can be used for farming and for civil engineering, but there are not human life involved.
Okay, thank you. I think it's very clear. One last question from Clodoaldo Faria Jr. It's a long question. He says he's building an SPP application, but his error in U is always too high compared to others, E and U. Getting about 4 times bigger, but only it gets bad. That said, do you know of any effects that might be causing this, any fixes that are missing?
But the question, you means that the solution that I shown for SPP is too nice? Is the error is lower than the other cases? Could you repeat the beginning of the question?
Yeah, the beginning. He is building an SPP application, but the error in U is always too high compared to others, E and U.
No, it's not too high. It's a very nice result here. Look at this. I'm going to share the screen. No, it's not too high. If he means this case, let me check. For instance, here, this is a really SPP, standard point positioning. To have this is without smoothing code, without smoothing code. To get in vertical component 3 meters of error is good, is very good. In vertical component, we can, it depends on the number of satellites in view. This is single constellation. This is using only GPS satellite, single constellation. This is I think that it was in Europe. And the error is typically less than 5 meters. This is a good result. It's not bad. in the current situation. In multi-constellation and smoothing code, well, it can improve, but not too much. Not too much. This is not a bad result. It's a nice result. Let's go to see the first slide. Here, this one. And show here. Look at this. In the horizontal component is about 2 meters. It's a very, very nice result. This is not, the result does not come from a mobile. If it was from a mobile, it would be worse because the antenna is worse. This is single frequency. This is using single frequency, not dual frequency. And it was a septentrion receiver with a pinwheel antenna. Pinwheel antenna is designed to reduce multipath. Then I confirm this is a very, very good result. I don't know if this was a question.
Okay, Clodoaldo, if you have any further questions, please send us. We will try to answer. Professor Jaume, thank you very much for your presentation. And we have now a quick break. I invite you to make a 5 minutes break, and then we will start with Dr. Adrià Rovira Garcia.
Okay, thank you very much, the audience, to attend, and thanks to you for the introduction. Thank you.
Thank you. So now it's 10:30 in Brasilia time. We continue at 10:35. Okay, in 5 minutes, 7 minutes, we'll be back. See you soon. Okay, we are back from our coffee break, and now we are going to see the presentation from Dr. Adria Garcia. And by the end of the presentation, we'll have the second Q&A session. So you can send your comments, your questions in the chat, and after the presentation, we're going to answer them. Dr. Adria, good afternoon. When you want, you can share your start and share your screen. I think your microphone is closed, but here, no, we have a problem with your phone. I will turn it off, and you turn it on, please. We can't hear you. Adria, please disconnect and connect again. Probably the problem will be solved. Thank you. Just 1 minute, maybe less, and Dr. Adria will be back soon to start his presentation. Okay.
Hello, can you hear me now?
Hello, we can hear you perfectly now. Thank you.
Okay, well, at least the audience got a couple more minutes as a break. So
yes, today we had to make a quick break. We are a little late, but it's okay. We can finish the webinar 10 minutes late. It's not a problem.
Okay, so let me share the screen.
We Adria, actually we only have a 4 hours limit, so we cannot pass this 4 hour limit. So
No
problem. Just to have this in mind, okay?
Okay, no, I will stick to the original time, no problem, because the tutorial is very long. So we will not finish either if we were on a normal on the schedule. You will see that we have a lot of exercises, we have homework, so we have many more material that what we can cover in the remaining time. So when the time comes, I will finish and then let the students continue afterwards.
Okay, perfect.
So no problem. Can you see my screen?
Yeah, we see your screen in the edition mode.
In edition mode, perfect. Let me try to fit everything. Well, maybe I can start. Yeah. So today we are in the fourth day, sorry, of the training, and we are now starting the second tutorial. And as you remember, on the first day, we had the tutorial number 1, in which we presented the GLab tool suite. We did the installation of the program and so on. So we assume, or at least I assume, that everyone could install the program and could run it. We did not receive, well, we received some feedback and of people having installed it with no problems. We are limited today with time, so I will just concentrate on the exercises. So Well, in this practical lecture, what we will do is we will see how the processing, how the positioning modes that Jaume was commenting on the previous lecture, how they work and how they, this lecture, this training is a hands-on training, meaning that what I do, I will be doing the exercises. There are 2 exercises that we will do together, and then what we want is that you also do the exercises simultaneously with me, so that and let's try. We know we are in virtual mode. That this is not like being all together in the class, but let's try to do this as interactive as possible. So I will be doing the exercises slowly so everyone can follow. If you get lost or something is not clear to you, you can write on the chat. I will have an eye on the chat so that we can go over the concepts and try that everything becomes very clear. For today, we will be doing the standard and precise point positioning. Recall, we have just seen in the previous lecture by Jaume the SPP and PPP. So let's first go to the standard point positioning, and then in this exercise, in this first exercise, we will analyze the different model components. Let me change this. Yeah, the different model components. So we have seen that there are measurements that have been generated by the receiver, and now what we will see is how do we have to take into account the different models of this signal propagating from the transmitting antenna on the satellite to the receiving antenna on the receiver here on Earth. Tomorrow we will do a receiver on a satellite. So we will do a satellite-to-satellite positioning. But today we will do a permanent station that is on the ground. And then we will see different error models that we have to correct. So I will use the term model or correction for today's training, for today's lecture. They are interchangeable, model terms or correction terms. In terms of the ionosphere, the troposphere, the relativity, effect, etc. And then we will provide an answer linking to the question that was some of the questions risen just before the break. And then we will have the opportunity to see why an error component is typically much better than the other two, and so on. And then I hope that you can follow the exercises on your site. Okay, so this is the first exercise. So we will be using these 2 files. We will be using a file that is a RENEX file. Remember that the measurements that are generated by the receiver, they are stored following standard format. The standard format is this RENEX file that we saw on Monday. And then we have a second file that is this broadcast orbits and clock file. And this is why you can see that is BRDC, and this is the short name for broadcast. And then we have some numbers. We have some numbers in both file names. This is a convention on how we organize the files in the IGS network, in any cartographic network that you might be using on later. You can see that we have the last digits. The last digits is the year. This belongs, the data belongs to 2004, and especially the first day of the year. And this is why these files, they have 001. And so it's the 1st of January of 2004. Just as a detail, maybe for the more experienced attendees, this other zero means that we have 24 hours of data. Sometimes if we have a shorter data collection, you will see here a number. If we only have maybe the first hour or the second hour or the 10th hour of the file, we can indicate here. Or even you can see also by quarters of hour, by fractions of 15 minutes, and then we use also letters. But in this case, we have 24 hours of data, so we have this 0. This is the station. This is the station that I show the first day. The CHPI, this CHPI station, it's located in the south of Brazil. And it's mainly, you know, and that this is the Cachoeira Paulista. Remember that it was a station in the middle of very green fields with very open sky conditions. So we should expect to have a very good, a very representative positioning. What is special of Brazil, as Felix commented in previous lectures, is that we have the first modeling term that we will see is the ionosphere. And the ionosphere is the upper layer of the atmosphere, and in the Brazilian region, we will see that is very active. And so this was a very good choice, not only because we are in the Galileo Information Center of Brazil, but to illustrate what the ionosphere can do. Okay, so basically, as we said in the first day, this is how the tutorial is thought. And so it is very self-guided, and so you only need the slides, and then we will be following the proposed order. And sometimes it's as easy as 1, 2, 3. Sometimes it's straightforward. And then for 5 and 6 to make the plots, and sometimes we will have to work a little bit. It depends on the exercise. Okay, so let's then go to the GLab. I will try to fit everything here. So let me rearrange a little bit my desktop. Yeah, I think this will do. Okay, so well, this is the GLab tool as we said, as we introduced on Monday. The GLab tool has, as we saw, it's multi-purpose. You can do many things. The different things that we do in the tool, they are guided, they are separated in the modes. We have the positioning mode, that this will be what we will be using today. So we use the tool to compute a position. 3D coordinates. It has another mode that is the analysis modes, that is to plot in a more friendly way, well, to plot the results. But we also have other modes, and some of them they will be explored tomorrow. Tomorrow we will be also comparing orbits and clocks, and so on, and some other more advanced modes that, for example, is to add add error to a RINEX files. So not only we can position actual RINEX file, but we can inject errors into the data, and then we can see how this translates into the positioning, and then we can do some other experiments. But today, let's start by the beginning. So we are in the positioning mode. Inside the positioning mode, there are 4 templates. Depending on which template we are using, we will be having one options or other options selected. Now, after the overview of Jaume, you know that all of these modes, from the absolute positioning, SPP, the differential modes, with code, that is the differential GNSS. If we want integrity, then we need to use corrections from an SBAS or a GBAS, and the PPP, the precise point positioning, that we will be dealing with detail tomorrow. Okay, so, well, I don't know in which template I am, although you always have here on the bottom side, you always have an indication of what was the last template that you use. This is just a template, and then, as I said on Monday, the user, you have full control of the tool. So the template is just an initial configuration that we think that makes sense, but you can always refine it to your needs. Imagine that I am discarding many satellites for whatever reason. Every time that I press the template, the tool will erase my choices and will leave the default ones. But then I can again select other options. So be careful. Every time that you press the template, you will lose all of your changes. Of course, you can save and load at any point. You can load these options or save these options to a text file. So if you need to interrupt your session, or you need to finalize and do something else, you can always save the options that you are working with in a text file. Okay, so let's then do the exercise. Otherwise, we will not progress. And let's then select the SPPP, the SPPP template. Then in the input section, remember that this is the GUI, the graphical user interface, mimics the processing inside the lab. This is why the leftmost tab configures the input, the input files that are going to be read. So let's upload these 2 files, the Brazilian station, CHPI, and the broadcast file. This is in number 2, and we leave everything else, all other tabs, we don't make any change, so we leave the default configuration, and the last step is to run GLab. You can run GLab from any tab. You don't need to be in the input or in the output. As you can see, we have performed the processing, and apparently nothing happened. We have only seen a progress bar being completed. If you click the Show Output button, you will see that then we open the output of the GLab. What is the output of the GLab? Well, if you go to the Output tab, you will see the path. You will see the path and a file name that by default is glab.out, but we will change it. You can use your name or whatever file name, and we will change this in a minute. What we have here and what we have in this file, well, you can see that it's a long text file. At the very beginning, it has an information section where it's telling us information about the GLab, information about the input files, information about the antenna and the receiver. This is an informative section. This is related with, you see here in the tool, you see the output messages. And these are all of the messages that are being displayed in the output file. So the first group, all of this first group, is the info. I need to be still with the mouse, otherwise, let me try to. Well, I hope that in your desktop configuration you can see the explanations. For example, this one, the MEAS message or the input. All of these fields correspond to the messages that we are displaying in GLab. So you can see that then we have this full traceability that I mentioned on Monday. So at every step of the process, we know what the tool is doing. Every of these fields, let me try to see with the input one. Every of these fields, maybe I need to be on this on the screen. All of these fields are, maybe here, are the files that are the columns with the model. The problem is that I have very little space. The epochsat, for example, the epochsat, if we can go here, and here we have the message epochsat, and here we can, if I overfly here we have the explanation. So you can see that the first field is the label, then we have the year, and then we have the DOI, we have the time, and the signal that we are using to position, and the 7 satellites that we are positioning. So basically, what the tool has done is a computation that, starting from the RINEX files, has generated an output file. Okay, so this was after the completion of the first 3 steps. Then let's go to plot it. Maybe some of you have already plotted the result. So basically, we have different templates. We have many templates. For example, if we press the button, the button here, the Northeast tab button, we will generate the plot with the results of the GIC-BR station. And here we have the Northeast tab, the north in blue, the east in green, and the up error in red. Then we can see that we have these 86,400 seconds, the 24 hours of data, and then we have for every, let me check, every 300 seconds, so every 5 minutes, all of these points are separated 5 minutes, 300 seconds. We have an estimation, and we have an estimation of the positioning error. And then how we can compute the error? Because this is a permanent station, and we know very precisely the coordinates. And when we are in the open field or with a car and we don't have a reference position or a reference trajectory, then it's much difficult to compute the positioning error. But in the case of a permanent station, it's straightforward. We can compare, we can subtract, we can make the difference of the obtained position and the reference position. And this will give us a difference, what we call the error, in 3D. We could do it in XYZ, but here we prefer to use a local system of reference based on the station that is in the north, in the east, and in the up. As you can see, the first warning. If we were in the classroom, maybe someone would ask, well, what is going on between the result that we have generated, the one that I have on the screen, and the result on the slides? They look very, very different. Well, we have to be careful about the scales. The scales in the plots can make the result appear very, very different. Here, if we go back to the analysis, you can see that I have the automatic limits. I have the automatic limits, so the plot fitted to the data. In the contrary, the fifth step told us to set the vertical range from -40 to +40. So here, if we write -40 and 40 and +40, and we redo the plot again, then we will see that the result looks much close to the one that we have in the slides. So this is just a warning, and when you are doing the remaining of the exercise, before and you see a discrepancy between the results that you have obtained and the results that are expected by following the tutorial, first check what are the scales that you are using, because they make appear our analysis very, very different. And this is my first recommendation for the remaining of today's tutorial and tomorrow's tutorial. So check always the scales. Okay. And this is what we did. This is the plot that nicely agrees with the tutorial. And if you look at the plotting tool, at this analysis mode, you can see, maybe it's better if when I press clear, here we have a clear button, and that resets everything to 0. You can see that this is the graphical user interface, and that has a limited number of options. But the tool is way more powerful. For example, here you can see that we can configure up to 4 plots. And so in the same graph, in the same panel, let's say in the same figure, we can plot up to 4 time series, because we think that with 4 time series is more than enough for the tutorials that we will be doing here today. So when you press Northeast tab positioning error, we are using the time series number 1, the time series number 2, and the time series number 3. But you can see that the time series number 4 is empty. So we could here include anything that we like. But to plot the navigation error with 3 plots is more than enough. This might look obvious now, but when we are doing more advanced plots, when we are departing from the templates, we will see that we need to understand a little bit how the plotting tool works. So this is just an introduction. Okay, so let's do the exercise. I hope now well, let me check if we have some questions. I turn the screen share a moment off so I can read the chat. Okay, I see that there is a question, but I think it's not related to this first part. But feel free to write your questions. Okay, let me then screen share. Okay, so let's go to the exercise itself. The exercise itself, we have to go to the modeling part. So we go back to the positioning, and then we go to this central modeling part. So basically, here you have to notice, and if you don't notice, I tell you to notice, that there are a lot of options that are unselected. This might be surprising if you look it from the first time, no, with a little bit cold, no, like why there are some options and why there are some options that are not selected. And so, for example, this solid tide correction, and that we will see not today but tomorrow or maybe if we have time, we can see today. What is this modeling term? Is it not important? Is it not necessary? What is going on? What happens if we enable this modeling term? Like, will we get a better error? So the errors that we have seen before will be smaller, or not, or maybe they become larger. I am trying to put lots of questions to make you think. The added value of the tutorial is to make you think and make you question the terms that we are seeing in the theory lectures. Otherwise, to see me touching buttons, it is not very appealing. So make the effort to think on these preliminary questions. Okay, so we have the default modeling, and these are the default terms that we consider in the standard point positioning, and this is what it is done in this standard. Then the tutorial tells us that let's disable the iono correction, the ionospheric correction. How do we disable the ionospheric correction? And the ionospheric correction is here on the middle. Here we can see that we have different models. We have the Klobuchar, that is the original model that is inside the broadcast by the GPS correction. We also have NECWIC, that is the equivalent broadcast model for Galileo. We have the Klobuchar, and we have for Beidou, and that is the Chinese constellation that is similar to the American one. And then we have two more ionospheric models that we could use. But let's disable completely. So no ionospheric correction. Okay, and this is the step number 1 that we have to do. And then as a step 2 is to go to the output, and change the file name. Change the file name where we will be writing our results. If someone has been very quick and has pressed the run button and the run GLab button, the bad news is that he or she will have overwritten the previous result. So if this is your case, please start from the beginning and then apply the full model to the glab.out file name. So we have in the glab.out, we have the full model, and this is why we put it in green in our slides. And in red, we have the glab1, in which we are missing one term of the SPPP model, the standard point positioning model. So then we have two different sets of results. Okay, so if we go to the analysis, if we go to the analysis again, and we plot plot the northeast tab positioning error, again with automatic limits, so we can check, we can do a first assessment Here we have the plot. This is different from the one in the slide because I did not set the limits. Here I still have the original result, also without automatic limits. We can see the that we have a different result. We have a different result. Okay, so let's now, okay, for if you want to follow strictly the tutorial, we can make the exact e-scale from plus minus to 40, and then we will get the result of the slides. Again, this is to show that the plots can dramatically change from one scale to another. Okay, so the question, what has changed? Do we see any change from using the full model or not using the full model? Well, let's answer this. We need to see it. Imagine that I have closed all of the plots, so I have very bad memory, and okay, I can recall that there has some changes, but let's try to at least quantify or put it black and white. Okay, so let's then follow the procedure. So let's click first the clear. So we set the graphical part, the plotting part to 0. So we start from 0, and then let's configure the plotting tool. So in the plot number 1, we will be putting the glab1.out. In the plot number 2, we will be plotting the glab.out. And so you can follow my steps, or you can follow your own steps in the slide. And we will reach to the same point. Let's put also the limits, minus 40 to plus 40, and then from the to plot the error, to plot the error, we need to select the output. From all of that rows that the program is writing, we will select those that start that have in the first column. This is what the $1 means. Dollar is the way we refer to the columns, and then we say that we are plotting only the messages that start with the word output. And then as an x-axis, we will use the seconds of the day, that is the column number 4, and as a vertical axis, we will be using this label, that is the column number 20. And the column number 20 is the up error. To make it short, the delta, the difference of the station in the up component. And this is what we refer by D esta U. So you can see this is the glab.out. So let's write something to distinguish the time series that we will be plotting. So for example, we can write full model. or original processing, or wherever you want, like full SPPP model, and with all the standard, with all the terms of the standard. To make appear the as in the slides, we need to make some static changes, like putting the same pattern, the same marker, and the same color. We want, at least with this first example, we want to exactly have the same result. Okay, so this is completed. The plot number 2 is completed, and let's configure the same for the plot number 1. You can see that they are independent. Whatever we do to the second time series we are plotting, it is not, it is different from the other 3, from the plot number 1, plot number 3, and plot number 4. Okay, so let's do the same. So we are plotting the output condition, and then we are plotting the second of the day, sec, and the 20th column, the 20th column, that is the up error of the station. And here we can put no ionospheric correction, to make it fully traceable, what we are doing. This is the GLab1. This is the GLab1 file with the ionosphere missing. And then again, some statistical changes like the dotted line and the red. And we use red because we are missing one of the terms. And I think we are ready. We could put more things, like the description of the label, and of the vertical and the horizontal axis. We could put also a title of the plot, etc. But this is not an exam. The exam will come tomorrow. No, I'm joking. There is no exam in the professional training. So there is no need to put everything. So let's plot it. Let's see if we get the same plot. And this is the result. And this is the result where we have the time series that we saw before. And well, we saw the 2 already, because when we press the northeast tab error, we were looking at the 3 errors. But here we are comparing the effect. We are comparing the effect of neglecting one of the models, and we are looking at the impact in the positioning. We can assess what is the degradation, because you can see that the errors, the errors in the when we are taking into account the iono are smaller, are closer to 0 than when we are not taking into account the ionosphere. That is the red correction. Sorry, the red, these red points. So if we make a zoom, we can see that this was not a smart choice. This was not a smart choice, because we increase the errors by more than 10 meters. Sometimes it is not very, very dramatic. So the errors, taking or not taking into account the ionosphere, does not impact so much. But there are epochs, and there are epochs in the day, in this 1st of January of 2004, in which we can pass from 0 meters of error to up to 15 meters of error. And so, in general, it looks like a good idea to have a ionospheric model. We could be talking a lot of what is going on, what is the difference between this region, and what is what is going on in this other region, in these other times in which the errors are more similar. I am trying to launch to motivate you to think. So we leave this, we leave this plot minimized somewhere, and we can do the same. We can do the same for the horizontal error. So basically we clear, so we restart the plotting. So we put the limits that are suggested in the slide. So we will plot a rectangle of -20 to 20 meters, and then in the second plot we put the GLab 1, no, the GLab 0, if we want to make it fully compatible, and then it's the same. We plot the output condition, the output message, and here we can write 19 and 18. This is a trick in order to be a little bit faster. This is just the 18th field. If you count them, you will see that whenever if I go here, the north, this is the 18th column, but if I write a number, it will match the column that we are plotting. Okay, this is the glab.out. So here again, I put full SPPP model, and I make some statics changes. So something like this, circles, blue circles. And in the plot number 1, we do the same, but with the file that is missing the Yono correction. So basically, we put the output condition, and then we write 19 and 18. And here we write no ionospheric correction to have it fully like the slide. So because we have one less term in the model, we put red circles. So this is everything is ready to make the plot, and we can launch this second plot to see what is the impact in the horizontal positioning. Why horizontal positioning? Because we are plotting the east error against the north error. It's like if we are cutting the error in an horizontal plane. Before, we were looking at the evolution. If we get the previous plot. Before, we were looking at the temporal evolution of the up error in the left plot. Now, what we are looking is at this error, this horizontal error. And so here we have 24 hours of data. Here also we have 24 hours of data, but before it was with the time, here was the north error respect the east error. Well, east, west, north, south. This depends if it's positive or negative. And I hope you get the idea. So now it comes the interesting questions. So it is not just following a tutorial, but this is just to make us think. And I pose this question to the audience, and I hope that you are first awake and second active enough to propose what is going on. Why in the vertical positioning, in the vertical domain, we see that there is a huge difference. There is a 10-15 meter difference between neglecting or not neglecting the ionospheric correction, but in the horizontal positioning, we can see that the degradation is not that severe. If I hide, if I don't write if I didn't write the labels, you would not be able to tell which positioning is which positioning. It would be very difficult for us to say the blues are the full SPP model, the red ones are the ones not having the iono correction. So let's now advance. I let you think. I let you think for a couple of minutes. And maybe I can minimize this better. And maybe giving you the next slide we can start guessing what is going on when you can start matching the points to answer the question, that what is going on in this result. In order to give a little bit, to add a little bit of light, we can plot the ionospheric content. We can plot, the model term of the ionosphere. And the ionospheric content, it is the ionosphere that was present that day. Here we don't have the tools to plot it. What we can plot is the prediction, if the prediction of the model, to see what is this magic that we are taking into account in the glab.out, and it's working very, very well in the vertical timesheet, in the vertical positioning. And when we disconnect, we destroy the vertical coordinate estimation. Okay, to do this, we need to press the model component. By default, we have the column 22, that is the relativistic effect on the satellite. And this is, but we are interested into the iono, and that is the field number 25. Maybe some of you have already pressed the plot button, and maybe you are worried. Let me make this mistake, that we can try to see what is going on. If you have pressed the plot button, you will see a 0 line. Why? Well, this is the model. This is the model that we are using in the second processing in the glab1.out. So we are basically verifying by doing this mistake, we are verifying that in the GLab 1 we are not using any ionospheric model. And you can see that for the 24 hours, the ionospheric correction is 0. If we want to see the ionospheric correction, we have to write, we have to use the glab.out. The glab.out is the file that contains the full model, including the ionosphere. And now, if we do it, if we redo the plot, what we see is the result of the slide. And this is the model. This is the model that we apply when we are using the Klobuchar model. If we were using the Nequik, we would have another shape, slightly different. The better the model is, the better will be our positioning. But this is what the Klobuchar model is predicting for that station, that day, and that year. You can see that the result is specular. You can see that there is a symmetry. There is a symmetry in 0. This is because the ionosphere affects differently the code measurement. For the code, these absolute measurements that Jaume was introducing in the previous lecture, it delays the code. So it is like if the satellite was with a greater distance. But for the carrier, we can see that the effect is negative. We have a negative value. It's like the distance to the satellite is shorter. Let's focus on the positive part. We are doing the standard point positioning. So in the standard point positioning, if we go to the positioning in the filter tab, you will see that the measurement that we are using is C1C. Is the course acquisition code. In the literature, you will see that some people refer to the civilian code to the first frequency. And so we are using the code. So we are interested then into the upper plot. And this is the prediction for the 24 hours of the 1st of January 2004 at this particular location, where we have the CHPI station. Maybe now, maybe some of you say, this pattern is familiar. Where we have seen this pattern. And let me try to rearrange the figure to make it fit. The pattern of the ionospheric model resembles the errors in the vertical component. Maybe it is, I thought it would be clearer to make it like this, but maybe in a small, it is better. Let me try. We typically do this in the Blackboard and with double projections. We are also new to this professional training edition. You can see that we can see. Let me try. only with almost positive errors, we can see that, or this explains why before second 20,000 we have very little ionospheric content. This is linked because at this time we have the night. We have the night. We don't have the ionization generating free electrons in the upper layer of the atmosphere, and this is why the model is has a low value, around up to 1 meter, 1.3 meters. This is why in this first part of the day, neglecting or not neglecting the ionospheric correction does not impact so much. But what happens? We have the sunrise, we have the sun going up, and then we have the full ionization of the upper layer of the atmosphere. And then we have a lot of electron content, and we can see that the model reaches up to 25 meters of delay for some particular satellites. We can see, and to give a number, look at the epoch 60,000, a little bit before, a little bit later, around 60,000, and we can see that when the model, we have this, then the ionization, neglecting or not neglecting the model, it really makes a difference in the positioning domain. We can see how this impacts, we can see the translation from the modeling to the position domain. I hope it's clear. Let me go to the questions to see if we have some questions. There is a question from Fabio referring to Linux, that the button is not working. I don't know if this is solved. It takes, the first plot takes a while. This is why it gets log. If not, you can send me an email. If this is an installation problem, we can work in offline. There is another question from Eugene that says that what does the number behind X column and X column mean? Yeah, this is what I refer. This is the columns of the output message. If you go to the positioning tab, I'm not sharing the screen. Okay, let me share the screen again. The question, if I understand the question right, is what are these numbers? These are, for example, the numbers associated to the model message. The model message, you can see it here. The model message is the, you see, well, this is, you can see it flashing because I am using a small screen. Let me try, if I go here to the very, I cannot even fit it. I hope your screens are bigger and you can fit all of the messages. If I select a smaller message, or I try to make it here. Let me try to see. Yeah, with the prefit message that is shorter and it fits my screen. Here you can see the the content of this particular message, and we have rows and we have columns. For the row with the starting with, in this case, is prefit, we have 19 different messages. And then message 1 is prefit, the column 2 is the year, the column 3 is the day of the year, and so on. These are the numbers. These are the numbers that you see in the analysis. Following with the prefit message. With the prefit message, we can see all of the different fields that we can plot. But we identify this by the number of the column. I hope now it's a little bit more clear. Okay, so this is the summary, and this is the summary. I went very slow with this first example, because the other examples of the session are to repeat the same procedure. And now that you have the methodology clear, you can go very fast, or you can do it as a homework. You will have this structure. Then in the following slides, you have this structure, how to make the plots, and then a part of a summary where we can trigger the analysis. We can trigger the discussion. And also, you will see that there are some backup slides with more theoretical content. So if we are talking about the ionosphere, or we are talking about the troposphere, or whatever component that we are analyzing, we have always some description of the mathematical part of what is going on in this physical effect. Here you can see these total electron profiles with the height. You can see that we have this maximum of electron content somewhere around 300 kilometers, and this is what delays or advances the signals that are traveling from the satellite to CHPI, from every of these GPS satellites to this permanent station. And that you can see that is in Brazil, and Brazil is a very active region because it's close to the geomagnetic equator. And we could be talking for the remaining of the week only of the iono, and you can see that the ionosphere has what we call the solar cycle, in which we have different activity periods linked to the status of the sun. And then you will see in the tutorial that how a lot of exercises, a lot of different exercises with the same idea. For example, I don't want to take more time. For example, for the tropo, we would come to the same. We would operate the same, and then we would arrive to the summary. And here we would also trigger some questions. Why the vertical positioning, what we see in red, it's more affected. It's more affected than the horizontal positioning. In a similar way than the ionosphere, you can think the troposphere is the bottom part of the atmosphere. The ionosphere is the upper part of the atmosphere, and you can see that the translation to the position is is in a similar way. Obviously not the same magnitude, but it affects more the vertical coordinate. And now it's time. Well, and then we have the backup. We have the backup slide with more information. Now, I just wanted to ask our audience what can be the reason, and this is linked to a question that was risen before. Why, with a normal tool, I think that there was an attendee referring to an SPPP software, and he asked why always the vertical domain, the vertical component, is always worse than the north and the east, the horizontal ones. I asked the audience, does anyone has any potential idea of what is going on? Why the vertical component is more affected? Or this is just bad luck of this data set and some other days or some other stations will show a different behavior? Please, any guess that you have, please write it on the chat, and then we can see if we have a clear explanation of not. We have a first answer that Thomas is suggesting that maybe it's related with the geoid models. But we can see that we are talking about meters. When we are using different models or refinements of the different models, the errors are typically smaller. It is the effect that we are seeing here. We are not changing anything related to the geoid. Here we are simply activating and deactivating a correction from the model, the ionospheric correction. But we are using the same system of coordinates. This what we are seeing is not related to the geoid. It's related to the Earth in some way, but it's not related to the geoid. But good trial. Any other guess? I see we have 40 attendees. Any other brave that wants to comment before we say the reason and then we close? Eduardo, I see that you are already here.
Yes, there is a comment from Thomas, but I don't understand what it's related.
About the geoid models. Yes, this is what we were commenting, that it is not, the effect is not related to the geoid. The effect, and now that there are only 5 minutes before I shut up, the effect is related to where the satellites are. Think the distribution of satellites. The station, we have a permanent station on the ground. So basically, we are seeing the satellites over the horizon. We are not seeing the satellites below the horizon. So the errors, the error of a satellite in the north might compensate a satellite in the south, or a satellite in the east might compensate a satellite in the west. But there is no error compensation between satellites on top of our user and satellites on on down the user, because the Earth is not transparent to the electromagnetic radiation. We cannot see the satellites from the other hemisphere. We can only track satellites that are over the horizon. And then the vertical errors are not compensated with errors in the vertical, but from the other side. Errors on the horizontal can compensate more or less. This is what you see in the horizontal plane, that errors in one side compensate errors on the other side, and we don't have a clear degradation. But for the vertical positioning, we don't get any compensation because we cannot track satellites on the other side of the world. This is not obvious. We have many of these questions. You are lucky because there is no exam. Our students here at UPC need to think in these kind of questions in the exam, but not in this professional training. So we ran out of time. We don't have time for a lot of questions. We only have 5 minutes until the professional training is over. I don't know if there are more questions from the audience.
Actually, we don't have more questions, so we can finish now the professional training. I think you can make your final remarks and maybe give an introduction of what we are going to see tomorrow.
Perfect. So my final remark is that you have the slides, you have the data, and you have the software tool. So now it's you can continue through the tutorial during today and tomorrow or the next week. This is not we don't have a strict deadline. And if you have any questions, you can write to me or to Jaume, and we will be delighted to answer these questions. Take my final remark is that take this opportunity to learn as much as possible. We have a very limited time. We are not in the class and so on. So take this as a homework. And then tomorrow we will see the PPP. You will see that the second part of the tutorial goes on PPP, the more advanced processing that will be introduced by Jaume tomorrow in the first part of the lecture. And in the second part, we will do the training, the third tutorial, and then we will put in practice this precise point positioning. This is everything from my side.
Okay, thank you, Dr. Adrià, for your presentation. We thank everyone for participating in this 4th day of the professional training. Thanks also to the speakers, Dr. Jaume and Dr. Adrià, and also André, who is together with us today. Well, we remind you that the materials are already available to download in the events website. The link is in the chat, and we await everyone for tomorrow, for the 5th and last day of our training at the same time. So, see you tomorrow. Bye.
See you. Bye.